Good evening and welcome to Perimeter Institute's public lecture series here in the Mike Lazaridis Theatre of Ideas in Waterloo, Ontario, Canada. My name is Heather Clark, Executive Director of Advancement here at Perimeter, and it is my sincere pleasure to welcome everyone here this evening, not only those of you who are here in the theatre, but those of you tuning in online. You have joined us at a very special time at Perimeter because just last week, we introduced Perimeter Institute's new director. It's exciting for all of us because the new director is also one of Perimeter's first faculty members, Dr. Robert Myers. Rob's appointment follows a decade of leadership by Neil Turok, who we are thrilled is remaining at the Institute as a full-time researcher. Rob has been absolutely central to Perimeter's growth and success over the years and will now shape Perimeter's bright future. So we thought we'd like to show you a short clip from last Thursday's very special announcement.
Our new director understands the incredible opportunities that await and how to capitalize on them. Understands that truly groundbreaking research happens through the collaboration of brilliant minds from across disciplines, across cultures, and across traditional boundaries. And our next director understands Perimeter, understands it perhaps better than anyone. Perimeter's new director, holder of the BMO Financial Group, Isaac Newton Chair, is Dr. Rob Myers.
I want you to save some of that, okay? Thank you, Mike. And thank all of you for being here today. Mike's idea was to create a new theoretical physics institute. It would bring together the best minds tackling the deepest and most difficult problems in physics. It's our privilege and our shared responsibility to make Perimeter fly, to carry Mike's founding vision forward with energy, with clarity, and with wisdom. Every one of us has a role to play. So everybody in this room who knows me knows three things about me. I like to learn, I like to listen, and I like to work hard. In this job, I'm going to be doing plenty of all three. And so, my friends, let's get to work.
So, we are very fortunate to have Rob with us tonight, and I would like to invite him to share a few words. Please join me in welcoming Perimeter's new director and the BMO Financial Group Isaac Newton Chair in Theoretical Physics, Dr. Rob Myers.
Good evening. Thank you all for coming here tonight or for joining us online. It's such a pleasure for me to be standing here tonight. I've been attending Perimeter's public lectures from the very beginning. Our very first lecture was way back in the fall of 2001. We had booked Roger Penrose, a giant in theoretical physics, into one of the largest lecture halls over at the university. See, we didn't have this big, beautiful building that we have here now. There was only one question for that evening. Would anybody show up? Well, the evening of the lecture came, and it started to rain, of course. On his way to the lecture, Perimeter's founder Mike Lazaridis found himself caught in a traffic jam right in front of the university. He figured, that's it. With this traffic jam on top of everything else, nobody's going to show up. But it turned out that traffic jam was people coming to see Roger Penrose. The event was completely sold out. So now, here we are, 18 years later, and more than 150 public lectures. Every one of those lectures has been sold out, no matter where we've held them. We sold out the University Theatre, we sold out our local high school. I can remember sitting in a room overlooking the municipal pool for a public lecture, and that was sold out too. But in 2014, we brought the lectures home here to Perimeter, and that allowed us to webcast them as well. Online, these lectures have been viewed by millions. I've always thought that this lecture series was one of Perimeter's first great success stories, and it remains one of our most important. That's because the future of science doesn't belong to scientists alone. Thank goodness. It belongs to all of us. Like you heard in the brief video, there's a role for every one of us to play, and that includes you. Your excitement about science, your passion for ideas, that's what energizes us as researchers and as a society. We are so glad and so very grateful that you're here tonight. Welcome.
Thank you, Rob. I'd like to take this opportunity to acknowledge BMO as a supporting partner for tonight's lecture. BMO for Women is supporting this year our women lecturers. Thank you very much, BMO, for your support. Tonight's lecture will last approximately 1 hour and will be followed by Q&A. For those of you who are watching online, we are fortunate to have Dr. Damien Pope, along with his team of PI researchers, online and ready to answer any questions you may have throughout the lecture. Please use hashtag #PILive if you want to join that conversation. I will also accept questions from the hashtag #PILive Twitter feed during the Q&A. And it is now my distinct pleasure to introduce tonight's speaker, Dr. Cather Simpson. Dr. Simpson is currently a professor at the University of Auckland with a joint appointment in physics and chemical sciences. She received her PhD in medical sciences at the University of New Mexico School of Medicine as a Howard Hughes pre-doctoral fellow. During her PhD, she became increasingly interested in understanding and exploiting the fundamental interactions of light with molecules, and she subsequently changed her career path to pursue this type of research at Case Western Reserve University. In 2007, she was given the opportunity to join the faculty of the University of Auckland and establish a new research lab, the Photon Factory. The Photon Factory is an award-winning research facility with a mission to achieve the extraordinary using state-of-the-art laser photonic technology. Her recent accolades include a New Zealand Teaching Excellence Award and the 2016 Silicon Valley Forum First Placed AgTech Medal. Dr. Simpson has been recognized not only for her research in lasers, but also for fostering innovation in undergraduate teaching, women in science, and ethics in education and research. Tonight, Dr. Simpson will discuss her own research, which explores the interaction of light with matter, particularly how materials can convert light into more useful forms of energy, and a relatively recent area of focus, its use in agriculture. So please join me in warmly welcoming to the stage Dr. Cather Simpson.
Thank you very much. I am going to talk today about farms, food, and photonics. I suspect everyone knows what farms and food are. We have experiences with that sort of thing, but not everybody necessarily knows what photonics is. By the end of this century, you will. So, photonics is the creation of light, the manipulation of light, detecting light, and using light as a tool to do really important things. And the growing importance of photonics has been recognized in 2015 by UNESCO, naming 2015 the International Year of Light. New Zealand was really important in getting this International Year of Light going. And one of the things I like about our New Zealand logo is that the Maori term for light, I'm going to mangle it, ma ramatanga, actually means illumination in the form of wisdom as well as the kind of light that's shining brightly on my face at the moment. We now have an International Day of Light, so May 16th, every year you can celebrate light and all the things it does for you. Now, I like to think of light and photonics in this way. This slide is so last century, right? The 20th century was the year of electronics, and if we think about electronics as the ability to tap into the power of electrons to do useful stuff, then that works, right? That's what we've got. The 21st century is going to be the century of photonics. Now, how many of you guys have a smartphone? Come on, everybody has a smartphone. A smartphone takes advantage of all of the aspects of light that you can see here. So light is an amazing, amazing phenomenon. It carries energy and it carries information. The single most important invention, I think, that allowed people to really take advantage of and use light was the invention of the laser. I may be a little bit biased. I think of this as being as important as the invention of the wheel. So the invention of the laser, which happened in 1960, really allowed us to start for the first time to control light. And this is your smartphone. So this is a photonic device. Over 100 components or steps in making a smartphone or making it work use light. Whether you're talking about welding in the battery, to cutting the case itself, or to the display. Okay, so every one of you is carrying a photonic device. You might not think of it that way, but it is. And lasers are everywhere. Light is everywhere. From gingivitis, which we now think is associated with Alzheimer's, you can now talk about light poverty and curing the world of light poverty, a way to raise up communities in rural places. You can remove tattoos or go to rock shows. And this slide illustrates both kitchen optics. So this is exactly the same phenomenon in jelly that powers our internet. And ambitious uses for light, like how do we use light to create fusion so that we can create more energy for the world? They do that kind of thing in America. Lots of big lasers all pointing at the same spot. And light is tremendously economically viable nowadays. So I put up this slide to show 2005, projected forward to 2020, and you can see that almost a trillion loonies, I put it up there just to say loonies, almost a trillion loonies by 2020 will be part of our economic landscape using light. In fact, it's really hard. Light is so pervasive now. This photonic technology is so pervasive. It's really hard to come up with these numbers because it's hard to dissect out where light is having its impact. Now, those of you who are a bit more tuned on than others might realize that at this point I've gone through about 10 slides and I've talked about photonics, but I have not talked at all about farms or food. So let me draw that connection now. We live in the environment of the sun. The sun gives energy to plants that are then eaten by animals that we eat, or sometimes we eat the plants directly. The sun is basically providing the earth with all of the energy that we eat. So you can think of the sun, essentially, as our food source. It just has to go through intermediate steps. And the role of photonics going forward is in farming and in food is to increase the efficiency of those steps so that we can more efficiently and green, with green intention, harvest that energy from the sun and feed the planet. And that's what I'm going to talk about now. Now I'm going to give you some examples. I'm going to talk about 3 different examples. And they're not all mine. The first one, in fact, is not going to be something I do in my lab, but the last 2 will be, and then we'll touch base at the end. So the first example I want to talk about is indoor farming. Now, at first glance, this doesn't seem to make a whole lot of sense. You know, you've got sunlight outside, you've got ground, you've got water, you've got everything you need to grow plants. In fact, that's most of our plants grow outside. Some of us, when we try to grow them inside, we're not very good at it. They just sort of wither and die. So why would you want to grow plants inside? Well, because it's got lots of potential for increasing our ability to feed the world sustainably. Okay, so this graph, you can see from here that growing plants inside, so indoor farming or vertical farming is what this is often called. This is from a Scientific American article. It's going to be a utopia when this comes. We'll have strawberries hanging in the air that are bigger than our head, and, you know. But the basic idea here is that if we get our photonics right, we can harvest energy from the sun. We can convert it so that we can use it for things like climate control, water control, all of those sorts of things. And then we can grow our plants inside, where we can control all of that stuff and grow them in a more dense way, and that will give us better food. So this is obviously a vision of the future, 2009. Well, I can tell you that 2009 on this chart is way over here. And indoor farming is growing like gangbusters. Okay? It's growing like gangbusters. But as I said before, why? Like, why would somebody want to do this? Well, the answer relates to this. So all around the world, this is a global phenomenon. When you have people, they want to eat. And the more people we have, the more food we have to produce. And this is causing us a real problem. Now you can see, so this red line here is the rate of growth of the population. So we reached kind of a peak, 2%, in roughly 1970, and it's been going down ever since. And that means our population is beginning to tail off a bit. Our population increase, if you will, is beginning to tail off. But here we are roughly today, and we've got another 5 billion people, if we continue on at this same rate, that are going to be on the planet wanting to eat. And that's a problem, because right now, just feeding the people that we have means that we have to have cropland the size of South America. And if we're going to have another 5 billion people, we have to add Brazil, and we don't have that much arable land. And on top of that, we're already at a point where in many places in the world, we've essentially depleted the resources of our farmland. We can't grow effectively in places in China, some places in Australia. All around the world, there are places. In fact, in New Zealand, the vice chancellor of my university likes to say that every square meter of New Zealand either has a tourist or a cow on it, and we can't get any more intense. So indoor farming ticks a lot of these boxes. The world is trying to become more sustainable. We don't want to have to, do the swift solution of eating the babies or anything like that, or tell people they can't reproduce. What we want is to be able to grow to that population size, feed those people, keep them happy, have everything be, affordable and clean. You want to have life on the land. You also want to have social justice. So this is UNESCO's sustainable goals. So the sustainable framework is now pervading what many scientists around the world are trying to do. And so, what are the advantages of indoor farming? Well, actually, if you take a step back and think about it, there are lots of them. Because you're growing indoors and you can grow vertically, you can grow with a lot higher density. Because you're growing with a lot higher density, you reduce the need for workforce. It doesn't take as many people to pick things. In fact, some companies are using robots. If you're growing things hydroponically or aeroponically, it reduces the need for water. You can begin to clean and recycle your water instead of running it through your farm and dumping stuff back into the watershed of your community. You don't need fertilizers. You don't need pesticides. And if you do need fertilizers, you can do it with precision. So it can reduce the amount of fertilizer. And if you're not using fertilizers, or if you are but you're recycling, then you're not dumping all of that nitrate and phosphate into the environment, so it's better for your environment. You don't have to worry so much about the weather. Imagine what raspberries would taste like if you didn't have to worry about rainstorms and hailstorms and wind and temperatures and things like that. And so on, right? So there's all sorts of reasons. And so I guess the question that I might ask is, well, why don't we have more indoor farming? And until recently, the answer to that question was money. So indoor farming requires that you enclose everything, you dump energy in. It's quite energy intensive, and when energy is expensive, then the farm products are expensive. But one of the things that's happened over the last 10 or 15 years that's made indoor farming really feasible is in photonics. So it's the ability to harvest light from the sun more effectively and to turn it into the light that we want to use more effectively. So the advances in the technology itself, but at the same time, the dramatic decrease in the cost. And that's what's allowing people to take advantage of all that indoor farming. It's actually photonics. So we'll look at artificial lighting first. So I love artificial lighting, you know, from when Prometheus brought us fire, you know, all the way through to today where we all have little LED lights everywhere, and in fact we worry about light pollution and shutting down our devices at night so that we can get good sleep. If you look at how light, artificial light has evolved over time, so notice this goes all the way back to the 1300s. This is in the UK. Light used to be really expensive, and that's because, you know, you had to get somebody outside to chop wood and build a fire and so on. Eventually we came up with candles. A bit strange to think about the invention of the candle, but it was transformative. 1800s, we're talking about gas and oil lamps. Late 1800s, we're talking about incandescent bulbs. Into the 1900s, the electricity system. We get very rapid advances since then, culminating in today, we've got the LED. And look at how the cost of lighting has dropped. And this is just 2006. It's continuing to go down. And that means that you can do this sort of thing. You can actually have a warehouse where you fill it with plants and you artificially light it. It's cost effective to do that. You can do more than that. It turns out different kinds of plants respond in better ways to different types of light. So this is just one example of a farm where they're using different colored LEDs to raise different types of lettuce to try to figure out what's the best. And if you go online, I'm not affiliated with any of these companies, if you go online, what you'll find is that there are a tremendous number of indoor farming, vertical farming companies springing up all over the place. All over the place. The one in the upper right-hand corner, right-hand corner to you guys is Canadian. And so that's all driven by light. But why aren't we picking it up faster? And the answer to that is that we're still not harvesting the energy in the same way. Okay? We're still not quite as good as we need to be in solar energy harvesting. So anyone who is interested in how we harvest energy to power the planet might want to have a look at this paper by Nate Lewis and Dan Nocera, written in 2006, still very important. They did an estimate of how much energy the world uses and how much it's projected to use going forward, and came up with something called the 15 terawatt challenge. So right around today, which is sitting in between here and here, it turns out that we, as a world, consume about 15 terawatts of energy. So that's the rate of our energy consumption. If you look at how much energy the sun dumps on the planet, in 1 hour, the sun will dump enough energy on the planet to power us for basically a year. But we're not able to harness all of that, and when we do, it's still not as cost-effective as it could be. Okay? We need to be able to do that better. Now, the two things that are allowing us to do that better, of course, are research and then translating that research to industry. So this is a very busy graph, but I love this graph because NREL puts this out every year. If you look, so here's Toronto, University of Toronto. Each one of these lines is a particular solar energy harvesting technology, and they're tracking how effective it's been in terms of percent yield over time. Okay, so the blue ones are the ones that you can commercially buy pretty readily today. So those are silicon solar panels. And you can see that they've gone from sort of 12% efficiency up into the 25% efficiencies. And at the same time, the cost of those have dropped. But look what we've got up here. We've got all sorts of new types of technology coming online. And these are up in the almost 50% efficiency. So that's really great. And if we look at what's happened over the last 10 years with solar energy, what we see is that in 1975 it was very expensive, so that's the orange curve, and not very many people had it. That lasted for a really long time. Okay, so this is the price, $101.05 per watt, okay? And all the way out until about 2008 or so, we still didn't have very much uptake of solar energy, even though the price had dropped dramatically. Well, right around here, the price gets to the point where the early adopters kick in, it's more efficient, it lasts longer, it's more mature, and suddenly now we're in this phase where so many people are getting solar panels. How many people have solar panels on their house? Anybody here? We're getting some on our house now, even though I live in a country that's called the land of the long white cloud. People used to say there's no way you could do this in New Zealand. And it's so interesting now and important that people are studying why that price of solar cells has gone down. So this is from an MIT group that's looking at why it's so much cheaper to buy solar energy now. And they've broken it down into what they call low-level and high-level factors. So the low-level factors are things like the cost of silicon, the size of the plant. And so you can see that actually the size of the plant is one of the most important determinants of dropping that price. Okay? In the high level, this is what your government does. This is when they subsidize your purchase of solar energy, or when you get R&D going into the slide that I showed you before. All of that work is R&D funding, and those sorts of things also affect the drop in price. And so that leads to things like this. This is really exciting. This is what the future looks like. So this is in the Australian desert. And Sundrop Farms, again, I'm not affiliated with them, I just think they're pretty darn awesome. They grow 1,700 metric tons of vegetables every year by harnessing solar energy, using it to desalinate water from the ocean, and to do climate control of their plant. Now, this is a greenhouse, so they're not using LEDs yet, okay? But they're using that seawater and sun to generate heat, cooling, and then make all sorts of vegetables for us. And fruit. Yummy strawberries. They're on the right track. And so the future, when my kids grow up and they want to do, put a garden in the backyard, they're not going to go get seeds and a spade and a, hose with holes in it to water. They're going to go to the, Mitre 10, the DIY store, whatever it's called, and they're going to buy a module. And that module is going to allow them to grow plants indoors. They're going to grow inside a box. They might use a greenhouse, but more likely they'll use LEDs. So they'll harvest the sunlight, turn it into electricity, control the environment, control the lighting, control everything, and grow their own vegetables, just like that. And so that's where this is going, this technology. Okay, so now I'm going to change gears. I've talked to you about photonics and farms a little bit, how all the achievements in lighting and solar energy have given us the ability to grow things indoors. And now I'm going to talk to you a little bit about things that we do in our lab, okay, in the Photon Factory. So when I moved to New Zealand in 2007, they didn't have a very short pulse laser facility. Nobody was really using femtosecond laser pulses for anything. So to calibrate you, femtoseconds are the same time scale on which the atoms are moving around in your body. So your water is doing a water dance right now like this. And all that motion is happening on kind of the femtosecond time scales. And what we were doing in the US, and then again when I moved to New Zealand, was basically using our lasers to kick those molecules so they dance a little bit faster, and then trying to figure out what they did with that energy. Now, we also wanted to have a bigger impact outside the research lab. And so the lab that I set up was designed to use those exotic laser pulses, those really, really short laser pulses, to help science at other places, but also to help high-tech industry in New Zealand. This is the part of the talk that sometimes is called lasers, milk, and sperm. And we also do meat and muscle beds, but I'm not going to have time to talk about those. So in the Photon Factory, you have to do really good fundamental research before you can do any good applied research, is my own view. We do a lot of fundamental research. We do what I call targeted research, where you're trying to improve some sort of process for industry, but you're not necessarily working directly for a company to solve an immediate problem. And then we do very entrepreneurial, innovative research. And I'm going to focus more at this end of the entrepreneurial side because that's where we're doing a lot of our research on farms and food. Now, I can't come to the Perimeter Institute and not put the word quantum up. We do quantum. So this is actually a really fun project that we've been doing where we're looking at the coupling of light and matter together. So that's a really kind of strange idea, new idea. The idea that you could take a molecule and change how it reacts by coupling it to light and creating new states. So this is some work by Rakesh Arul and a collaborator who's the synthetic chemist. Rakesh is headed off to Cambridge to get his PhD in a bit. Hopefully we'll write a paper first. And this just shows how we can do that light-matter coupling and where it puts us on the scale. I love this graph. You know, you've got Caltech down here. As time goes on, we're up here. That's us. We have line envy. We're like racing to try to get just above that line before Rakesh leaves. But this is really fun, okay? And this is the kind of fundamental stuff we do. So really deep, not very applicable. We motivate it by saying, oh, we're going to make catalysis faster and so on. But actually, this is about understanding the deep details and learning how to control and do experiments and ask the right questions. The more applied stuff is the reason that I end up standing in places like this. So we've done roughly $30 million worth of work, either funded by the government or funded by industry, to directly address problems that are facing the real world, okay? And to calibrate you, that's about $6 or $7 for every man, woman, and child in New Zealand. So it's like everybody missed a cup of coffee and put it in our lab instead. It also leads to things like this. So this is the Prime Minister, the former Prime Minister. You guys have a very sexy Prime Minister. We do too now. But at this point, Bill English was our Prime Minister, and he came and made a funding announcement in our lab, along with the Minister of Science and Innovation. And that's my son, Henry, who got a selfie out of the thing. I was still a little shocked when he just reached up and put his arm around the Prime Minister. I was like, oh my God. But, you know, he was very... And we're also... in a couple of years ago, we got named Ministry of Primary Industries Champions, you know, so I feel like I should be wearing my underpants on the outside and I should have a cape or something, right? But that's because we've been using our physics, all of that stuff we do with lasers and light matter interactions and how we control light to help agriculture problems, okay? And how do you do that? Well, you listen. So in about 2011, a dairy investor took me out for coffee and said, there are 5 problems facing the dairy industry, can you help? And I thought, sure, why not? Yeah, why not? And chose sperm sorting, of all things, right? That's totally obvious, isn't it? That if you're a laser person, you would be thinking about sorting sperm. Well, we formed a company called Engender, and Engender is now a real company that sorts sperm by sex for the dairy industry. So I'm going to tell you that story. So for her to make milk, she has to have one of those, but not all of those are equal. And the number one genetic determinant that a dairy farmer would like to control is the sex of the offspring. And so our company is set up to do that. So we designed our technology to use microfluidics. So this is channels the size of a human hair. Inside those channels, the flow is all laminar. So there's very little shear stress on the cells that are in those flows. The cells come into the microfluidic channels. They're stained before they come in for DNA content. Now, it turns out that the X chromosome is just a little bit bigger than the Y chromosome. So when you make them glow, the females are a little bit brighter than the males, which is not that hard to remember. And so the cells come into the channels. We use a laser, right? Light exerts a force. Turns out sperm cells are really shaped strangely. I'm going to show you the effect of that in a minute. But they're about 10 microns by 5 microns by 1 plus a tail. So it's like trying to sort a frisbee. So we orient them in the channel using a laser. We then use another laser to make them glow, to make them fluoresce. And then the key here, the new part of our technology, is that we use a laser to actually nudge them inside that channel. This is what it looked like a few years ago. Here's our microfluidic chip. You can see we have optics and nanosensors and pumps coming in. We've got imaging things to look at what the cells are doing while we're moving them around. The business model is you've got something about the size of a Xerox machine, a big one like that, a desktop one, and these chips are consumables. You make them for $10 and you sell them for $1,500. Okay? Not bad, eh? What's the physics? Well, it turns out light imparts a force, so everybody who's got glasses on right now, you know when they start slipping off your face? No, it's not. The force isn't that strong, but it could be. It's because you've got light coming in, it changes direction, and you know F equals ma. Acceleration is about changing direction as well as speeding up and slowing down. And so essentially what you're doing is you're using the transmission of light and its changing direction to impart a force to a particle. And you can think about that force in 2 ways. There's a force that essentially pulls the particle into the center of the beam, And there's another one that sends it shooting off in the direction of your laser beam, if you get the optics right. So anybody who's heard of laser tweezers, it's the same kinds of forces that are used in laser tweezers, it's just we've got it set up a little bit differently. This was one of the Nobel Prize-winning scientific areas last year. So Arthur Ashkin is the guy who invented laser tweezers. It turns out these guys invented a particular type of femtosecond laser that we use in all of our fundamental science. So, you know, this is like the photon factory's Nobel, no, we didn't win the Nobel Prize, but we use all of that science, which is very cool. Oh, so now I'm going to show you how it works. So you've got, I'm not allowed to show you sperm cells for commercial reasons, but you've got 10 micron beads that are coming in from this side. You've got a laser that you can't see here, but you can see as the beads flow down, they're getting moved up against that wall. They're being moved in the channel. Now normally we don't make them move all the way over to here, but this makes a nice video. Because we're physicists and engineers, we actually track all of that. And I can tell you that in that particular example, we had 250 piconewtons of force moving those cells around. To calibrate you, an apple in your hand is about a newton. So 10 to the minus 12th times that amount of force. And that's because they're microscopic. It's the same kind of force that NASA uses to move sails in space, and we're using it to move cells inside of these microfluidic chips. One of the challenges is that sperm are really complicated. So I told you they were flat, but look, this is the head of a bovine sperm. Look how flat that thing is. It actually acts like a waveguide. So it does like a fiber optic. It traps light. And so that means that if you watch a sperm that's been fluorescently stained, if you watch it swim under a microscope, it rotates like this, and it basically flashes at you every time the flat side comes by. And so that means we have to be really careful about that orientation. Whoops. So here's an example where we've got a camera on one side and a camera on the other side. So imagine if I'm a sperm cell, so that's my tail. And I'm swimming down a channel like this. I've got a camera up here, and I've got a camera back there. And when my flat side is to the camera up there, I get a nice bright spot on that camera. And when my flat side is to this camera over here, I get a bright spot over there. Okay? Most of the cells are at other orientations, and so they're down here. So how are we going to tell them apart? I told you the X is a little bit brighter than the Y. Well, this is some real data. These are dead cells, so don't worry about that. There's that bright bit of unoriented cells. But if you look over here and you squint and do a lot of wishful thinking, you can kind of begin to see two lobes. And if I highlight that, then I'll tell you that those are mostly X-bearing sperm cells right there. And so the better job we do of this, and the more we can move these cells out here, the better off we'll be in terms of our sperm sorter. So why would you do this? Well, because it's really good for the economy. So I don't know how many of you guys know this, but there are very, very few dairy cows that are inseminated by a bull these days, not directly. It's almost always done by some guy with a very long glove on, you know, and, and standing behind a cow, and you choose the genetics of the bull. And so artificial insemination is a huge business. Now, right now, only about 3% of dairy cows use sexed semen. If we can do what we say we can, in 5 years it looks like it might be half or more, which is really exciting. Now for me, I'm a university person. It doesn't mean I don't like money, and I'd certainly stop and pick it up if I came across some, but it doesn't tend to be my primary driver. For me, this is really exciting. So it turns out it takes 8 Indian dairy cows to make the same amount of milk as 1 US dairy cow. It's about 7 to 1 for India versus Canada, okay? And that's because in the US and Canada, in the OECD, we've been using genetic acceleration through artificial insemination for yonks. India has more dairy cows than any other place on the earth, 45 million. And all of their dairy cows are not very productive. So think about that. If we could improve the productivity through sex selection of the Indian dairy cow industry, we could reduce the impact of dairy on the environment while still giving the Indians a really amazing source of milk. And so you can look at projections like this. So this is a graph that essentially is basically milk per cow on this axis and number of cows on that axis. And it's looking at projecting, whoops, it looks like it's cut off at the end. It's projecting what's going to happen by 2027. And by 2027, you can see that India is projected to have a whole lot more cows, but they're not going to be very much more productive. Whereas China is predicted to have fewer cows that are much more productive. And so our technology is designed to be able to drive dairy in that direction. How do we continue to make more milk so that kids can get the protein and fat they need to grow, and at the same time reduce the impact of dairy on the environment? So where is Engender today? So Engender, like I said, started around 2011, 2012. We were in the middle of a Series B fundraise at the end of last year, and so we had met a really important technical milestone in the end of 2017. That was quite exciting. We did win a bunch of awards, so the gold medal in Silicon Valley was for Engender. And then we got acquired. So an international animal genetics company, herd improvement company called CRV, which is based in the Netherlands, essentially came in and bought Engender, which was very interesting. As I said, the original business plan was kind of manufacturing. We were going to make chips at $10 each and sell them for $1,500, and it was kind of what you call the razor blade model in companies. So that's how we were going to make a lot of money, right? Now what we want to do, CRV, is all about better cows and better life. And so CRV is driven to make a really great sexed sperm semen option for farmers so that we can improve dairy all around the world. And I like that. That certainly is more in line with my own values. So this is exciting. My next job, so up until December 31st, I was a university professor who also had a spin-off company and worked in that. And now I'm leading a spin-off company to turn this contraption into a product. And I am a university professor as well. So we'll see how that goes. It's very, very different. And that's the Engender story. That came from sitting over a cup of coffee with somebody who said, here's a problem, can you help us fix it? The next story I want to tell you about is called Orbis. So Orbis is a story about point-of-cow diagnostics. So every dairy farmer would love to be able to say, that cow, Maisie, has an udder infection. I can't see it yet in my milk. Buttercup puts the most protein and fat in my milk. Right now, farmers get that kind of information at a herd average, so they tend to get a test done every time the milk truck comes and picks up the milk out of the vat, and it tells them what's going on an average, but that means they can't really drill down and see it on an individual cow-to-cow level. And Orbis is designed to do that for them. So you remember the picture of the lab on a chip for Engender? You know, that was actually chip in a lab, wasn't it? You know, it's got this chip and it's got all this stuff. You're never going to put that in a dairy farm. How many people have ever been to a dairy farm? Yeah, that's right. So can you imagine having nano pumps and all of that stuff underneath every bale, every milking? As soon as she evacuates herself, your entire system would just be ruined, right? And so we had to design something that was more robust. And the way to do that is to use the physics of a spinning disc to control all of your flow. So Orbis uses microfluidic technology, but it's about sampling and sensing, not so much about forces, okay? And the way it works is, you can't tell just from looking at this, but this is actually spinning at about 3,000 RPM, okay? And the milk is coming in the middle, and you can see it fills up here and gets spun down into here. We can put different chemicals in the different chambers. We can put lasers in to read out what's in each of those. And the technology that allows us to do that is the same technology that's in every one of your cars right now if you have a CD player. So when you want to look at a particular type of metric, like protein and fat content, you put in one disc. When you want to look at progesterone, because you want to know whether it's time for Daisy to be made pregnant, is she ready? Then you put in another disc. It's the same as whether you do classical or pop. You don't change the reader. So all of the innovation and novelty is on the disc itself. And it's hardy and it's robust, and it's because we're using all that physics associated with spinning and rotating and acceleration and deceleration and so on. Farmers want this. That's because The global cost of mastitis is really high. In New Zealand in particular, we have a cyclical farming system. So that means if a farmer misses pregnancy at the very beginning, they've lost an entire productivity of milk until they can get the cow pregnant again, and that shortens how much milk they're going to get out of that cow this year. It's the same for other places where you guys probably go year-round. Certainly in the US, they go year-round. You don't lose quite as much. And of course, you'd like to be able, as I said, to pick the cow out of your herd that you really want to breed with that top bull. And you want to make sure, using engenders technology, that you make a girl out of that. Right? The cow that's not doing so well, but you're not ready to cull, you want to maybe breed her against a top beef bull and make a boy. And you want to identify her early, before you spend a lot of money feeding her and raising her up. So as I said, we use, in this case, the photonics is all in sensing. So we basically use light. You remember how I said we use our lasers to make molecules jiggle around, and then we look at how they jiggle? That's exactly what we do. That pattern of jiggling, those vibrations, are related to the composition of the material itself. And so this is actually a spectrum of milk. A laser has come in. We've then collected the light that comes back off the sample, and we've plotted it as a function of frequency, and in this particular case, it's telling me that I have melamine in this sample. This is not everything in milk. Milk is really complicated, over 10,000 different molecules. And so milk is one of the most complex fluids there is out there. And so using these lasers to probe milk means that we also have to use fairly sophisticated data analysis techniques. So we do quite a lot with that, and we're actually moving into a machine learning space so that we can train our algorithms to be able to pick up things like the different fatty acid distributions. We can tell you whether a cow's been fed on grass or on grain. We can even tell you how much supplement by palm kernel they've had. We can tell you whether that cow is good for making Greek yogurt or is really good for making cheddar cheese. And that comes because all the details in the amino acids and the fatty acids, that's all the compositional detail that all comes out when we kick the milk with a laser and then collect the light that it gives back to us. The person who really leads this and is probably one of the world's experts on the composition of milk in my group is, her name is Michelle, Dr. Michelle Newwood. And a lot of this know-how came from working with Fonterra and Milk Test New Zealand. So Orbis also won a prize. So I don't usually put pictures of myself up in slides, but in this case, it was really fun. I still have this big old check. Getting it back to New Zealand, because this was in California, was really fun. We came in third. And the future is about putting all of those different tests on the disc. So we've got fat and protein kind of sussed out. We're about halfway through being able to do progesterone, and then we'll partner up with an engineering firm and start looking at other things. One of the biggest advances or advantages of this technology is that we'll be able to test for things that other people don't even know that you want to test for yet. How many people have heard of A2 milk? A few? Yeah. So some people think it's a hoax, but the bottom line is that you should be able to tell the difference. 5 years ago, nobody would even imagine what A2 milk was. Okay, it's just a different variant in the composition of the milk. And that's Orbis. So what I've basically given you is a brief overview of 3 different ways that we use photonics in farm and food. The first one is thinking about how to harvest solar energy, convert it to electricity, use that electricity then to control the environment, to desalinate the water, to recycle the water, all the pumps, all the cooling, all the heating, all of that sort of stuff. That's indoor farming. That's coming, and it's coming fast. The second one was about using light as a way to generate force. So here we're using our light to move cells within a microfluidic channel as a way to sort them out. So we're using this for agriculture right now, but this has implications for things like blood dialysis. Imagine if you have a disease where you've got activated T cells. If you could hook yourself up to a machine that read which ones were activated and kicked them into a different channel and put everything back into your body, that would be amazing. And the third one is about using light as a probe, using light as a way to go in and say, what is in that sample? Can we use it to tell whether there's something in there that there shouldn't be? Yes, absolutely. Can we use it to tell all of the intimate details of what's in a very complex mixture so that we know what to do with that mixture, how to best use it, and then how to better improve our food? And so I hope what I've convinced you is that photonics, which is, physics at its best. It's all about the wave and the particle duality associated with photons. How do we create light using lasers? How do we manipulate it, move it around, change its shape, change where the energy is, change the field? How do we detect it? How do we use it as a tool? That actually it's all about, or it is able to, I should say, make the people and the planet better. Serve the goals of the sustainable development. So it remains for me to tell you a little bit about the people who do this work. So the Seaman Demons are the people that work for Engender Technologies. And these are the four kind of people who are on the leadership team at the moment. We have a bunch more, including business people now, and we're growing very fast, so I don't have pictures for everybody. Orbis Diagnostics actually started with the guy who sits next door to me in Auckland. He is one of the founding scientists of the home pregnancy test. And so the two of us came up with this idea for doing this in milk. That's our business team at the top and our R&D team at the bottom. These are some more members of the Photon Factory. I don't want to make you feel bad, but actually this picture was taken in my backyard at this time last year. So this is what it looks like in New Zealand right about now. And it only remains for me now to thank you very much for inviting me to give this lecture and for your attention.
Thank you so much, Cather. Wow, fascinating. I think we're all going to stare at our milk in a little different way when we pour it on our cereal tomorrow morning. We're now going to open up the floor for questions. The microphone is right over here, and I would just ask that you limit your questions to one question and make sure that it's concise and on topic and relevant. Thank you so much. Yes?
Hi. Thank you for the talk. I have a practical question. I'm not sure if you can answer it for, about your process. But so you have laser vibrational spectroscopy with DIS. How do you calibrate so that the farmer doesn't have to calibrate this process, so that each one, your results are going to be accurate every time that you do your test?
So you've actually picked out exactly the thing that we've been working on for the last 2 years. So the calibration is really important. And so there are a couple of ways to think about how you calibrate. One is that we know a lot about the composition of milk, and we're sitting in a chemical sciences department as well as in physics, and so we can break it down into its components and look at the signatures of each one and then compile it all back again, okay? The other is that you can take those spectra and then you can do analysis tests, chemical analysis, completely different way, to get, say, the protein content and the fat content. And without trying to identify which peak in the spectrum is giving you exactly which protein and exactly which fatty acid, you essentially correlate the shape of the spectrum with what you get from your chemical analysis as your gold standard. And that's the way that we've been going. So we've been using that kind of gold standard as a way to train our computer to recognize C14 fatty acids versus C12 versus C10 versus other things, right? And to essentially light up whatever that complicated pattern in the spectrum is that tells us what that component is. Yeah, that's a really good question.
Thank you.
Thank you.
I've got some online questions. Does vertical farming only apply to crops, or can it work for dairy, poultry, and swine too?
Wow, that's an interesting question. So I think in many places you would say that we're already kind of doing vertical farming for livestock. And it gets kind of a bad rap. If you look at, say, the United States and you go visit a dairy farm, you'll often find that the cattle are on concrete blocks. They never go outside. In some sense, that's intensive. It's not vertical, like we're not stacking them on top of each other. I don't think they would Yeah, but it certainly is intensive. You're putting them in a much closer, much more dense space than they would want to be in the sort of natural world. And that generates all sorts of problems, but it also, I think, informs what we're doing with the crops. So some people have merged things like aquaculture with agriculture in a vertical way. So there you might be growing fish in your fish farm and using the effluent from the fish to help fertilize your lettuce farm on top. And so those sorts of things are certainly happening. Yeah.
Okay. Another online question. Will vertical farms be able to produce staple crops like wheat, rice, corn, and beans?
That's an excellent question as well. So yes, some people are in fact using those sorts of techniques to do more intensive farming of staple things like wheat and corn and things. It's not quite as natural. So the things that are coming first are things like berries. So that's why I mentioned Driscoll's berries. Probably everybody's had Driscoll's berries. They're one of the biggest farmers of Driscoll's, of berries. You know, and imagine what the flavor of a raspberry if you didn't have to think about how long it sat on the shelf. You know, if you had the raspberries growing in the building next door and you could just walk over and they were only bred for flavor and texture, wouldn't that be amazing? And so things like berries and things like leafy plants, kale, lettuces and things like that are the ones that have come along first. Tomatoes are big as well, so.
Thanks so much for being here tonight. My question is surrounding the growth of the cultured meat and cultured dairy industry.
Yes.
And if you see that as a competitor or as a potential partner for your technology.
I certainly would not slow down the growth of cultured meat or artificial meat. Now, do I think we're going to end up having that on our steak, you know, on your plate when you go out for a steak? Probably not. But it wouldn't surprise me if 10 years from now McDonald's hamburgers weren't made from artificial meat, essentially. And you won't be able to tell the difference. And with a McDonald's hamburger, that's not what you're really there for anyway, right? You don't go there to get high-quality meat. I'm not saying it won't be high quality, that came out all wrong. But I think that in the fast food industry is where you're going to see it gain traction first. And of course, you know, you can already see it, like when I flew over here and I was in the airport, you know, I could go buy an ultimate burger or whatever it's called, an Impossible Burger, that's what it's called. Yeah.
Okay, interesting, thank you.
Hi, thanks a lot for coming. Anyway, my question is all light equal in terms of you had different wavelengths of light, different colors affecting the different plants. And I wondered, how do the wavelengths affect the growth? Is there any difference? And is there any difference in maybe the efficiency of the, you know, the photon effect, like the chloroplasts?
Absolutely, absolutely. So different plants respond to slightly different color palettes of light, and they grow at different rates depending upon what color is on them. We're still understanding quite a lot about that. So the picture that I showed you from the Japanese group was actually from a university where they're testing out how those different colors of light affect the growth of the plants. We still don't know as much about it as we would like. Most plants grow, you know, across kind of the visible to UV spectrum, and so, but where they're growing in that most efficiently is very exciting. Yeah.
Can I ask one more? Is moonlight any different than sunlight? Because you hear about plants that are harvested in moonlight and they, you know, flower in the moonlight. Is there any difference?
So moonlight is different from sunlight in that it's reflected off the moon. So it's the same photons. There's no difference in terms of the properties of those photons. It's got a different spectrum, so it's just going to have a different series of wavelengths. Yeah.
And that would affect the plant.
Yeah, absolutely, absolutely. Yeah. Good question.
I have another good question online. Can some of the sensing techniques you described be used on humans to detect illness or genetic problems, and is it happening already?
So, the title of this was Food, Farm, and Photonics, but you know that woman I showed you who's our expert in milk? She now has a grant to do the same kind of thing with a handheld device that will diagnose and type the type of skin lesion that you have. And so she's in a 3-year, $1 million project to develop proof of principle using the same kinds of ideas that we're using for milk, but basically so you can go up to, you know, grandpa who won't go to the doctor and say, Grandpa, go to the doctor. And so she's in clinical trials right now, looking at ways to take those complex spectra. I'll just give you an example. Turns out there are two forms of lupus, a particular type of lupus, one of which causes disfigurement, deep scarring, and the other doesn't. And at the moment, doctors can't tell early enough which one you've got, but she can with her spectroscopy. The other application that she's working on is for things like the pancreas. So if you go have pancreatic surgery, the pancreas is a really twitchy little organ, and it dies off at the edges when you cut through it. The lack of oxygen, it's very sensitive to that. And if the surgeon goes and sticks it back together, stitches it back together through tissue that's not healthy any longer, it will just come apart. So right now, surgeons go and they do their best visually, and then they go have a cup of coffee for 40 minutes or whatever to see if they got the right margins. She'll be able, using that same technology, to go in and find the right margins so that those doctors can stitch that up. And that's just the stuff that's happening in our lab. This is happening all over in the medical fields. It's very cool.
Hi, Cather. Great talk.
Thanks.
Could the Orbis technology be used to differentiate nutraceutical properties or even flavors in milk to give consumers their own flavor that they like?
Yes, so that's a really interesting question. Some people think that the dairy industry is going the way of like the wine industry and the juice industry. You know, it used to be you'd go to the supermarket and you'd walk up to the aisle and you'd buy orange juice or you'd buy apple juice. And now it's like, I want apple juice that was harvested in the midnight by, women only wearing pants. And you know what I mean? It's like there are 50,000 different types of juices. And people are imagining, some in New Zealand, that, you might wind up going to your dairy and saying, I would like to buy some milk with a fine Waterloo nose, And you'll buy regional variants of milk based on the flavor palette and the composition. That content. And so yes, that a lot of the things that we're detecting are the things that you can taste. Anyone who's had milk from a cow that was in a pasture that had garlic or onion growing knows that you can change the flavor of milk. Yeah.
Okay. Well, a great talk indeed. We so look forward to hearing more about your work. Thank you so much.
Thank you.